Okay, in this lesson we're looking at rotational solids and finding their volume. The key is still going to be finding the area of a cross-section. The difference is how these are formed, but these are a little bit easier in that they will always be dealing with circles. So they come from rotating some function around an axis. So this particular one is taking this curve here, whatever equation that is, and it's rotating it, spinning it around this axis so that it gets copied down here and forms circular cross sections. Okay, let's say we have a graph of a parabola here, and we're enclosing a region between the y-axis, the line y equals 1, and our curve. What we're going to do is we're going to rotate this thing so that it goes around the y-axis. Now as we're rotating it around, notice that at each point it would form a circle in there. If we spin it really fast, we start to get an idea of a solid that might be formed from that. Taking a closer look, as that's spinning, it would form a solid that looks something like this, where all the cross sections, since it's rotating, are circles. And each circle in this is defined by the radius at the particular spot where we are on the figure. And so again, we look at these cross sections here, and the radius at each point for each of these circles is going to be, in that particular picture, the width or the x value that we're looking at. The height then, if we look at each one of these as a cylinder, is going to be yard change in y. And so we're going to use dy in that particular picture. Now I might also choose to rotate this in different, or take a different region. In this particular problem I'm looking at this region right here that I've shaded off, and I'm going to rotate it this time around the x-axis. So notice my shape's a little bit different. If I'm coming out and rotating it around the x-axis, it would fit inside there like that. Notice how my axis is running, or my axis of rotation is running right along the x-axis as I turn this so that this upper side matches the curve. Again, the cross sections are all giving me circles, and each one of those circles has a radius defined by, this time, the y value, which we could write in terms of x, because each one of our things, the thickness of each of these cylinders, or these discs, is a change in x, and so we're going to use dx in our equation. Now since each cross-section is a circle, if we consider the area of a cross-section, which is our key to finding volume, then each one of these is going to be based on its radius. Looking at the picture here, we should be able to see that the radius is based on the value of f of x. It's the same as f of x. So in this problem here, our radius is simply f of x, and the area of a cross-section, being a circle, is pi r squared, or pi f of x squared. So if we have a formula for the curve, in this case 2 plus x cosine of x, then, and we think about those cross sections as being circles, and we also, if we are given limits of integration, in this case we're going from -2 to 2, we can find the volume. So begin by sketching your curve, and then kind of reflect it over whatever your axis of rotation is, and then fill in the circles that create it. Our next step is to consider the formula for a of x, and again these cross sections were all circles, so it may help to draw that cross section. Draw in your radius, and then note that your radius is equal to your f of x, or in this case 2 plus x cosine of x. Since we're looking for the area in terms of x, we're going to use pi r squared, but our radius is this whole function squared, so we need to put all of that in parentheses. So we have that. Our next step then is to find the limits of integration. Those were given to us as -2 to 2. And then we're going to integrate to find the volume. Remember, the volume is equal to our integral involving the area of the cross-section. Now, something you can do with these rotational solids is you can pull the pi out in front since it's a constant multiple. And then in this particular problem, we're going from -2 to 2. And then our radius squared will go inside. We could then finish this one on our calculator, but the most important thing right now is how do we set that integral up. So something to consider is whether we should be using dy or dx. And it's always going to be about how those discs are being sliced or how they're stacking. Notice in this one all of our circles are going in this direction. So those are all dx values because our slight changes here are slight changes in x, so that's dx. This one here though, all of these slight changes that we're looking at are changes in y. So we're stacking along the y-axis, and so those are dy values. So anytime we're stacking this direction, it has to be in terms of y. One way to remember it is if we rotate in a if we're rotating around a vertical line, then it's going to be y values. If we're rotating around a horizontal line, then those are going to be dx. And we'll do everything in terms of x. So let's just look at this one more example. These are the ones that we did that I had the solids for. Both of these are using the equation y equals x squared. And they're all being enclosed within the first quadrant. So we're really only looking at this part of the curve. Now this is important because for this one, we don't want to use both sides of this because we only need to rotate the one curve. As we rotate around this axis, it's going to give us both sides on that. Okay, it's going to go 360 degrees, and so that'll give us the full circle. We only want to use one side of it, of that curve. Okay, for the first one then, since we're slicing in this direction, those are dx changes. And since we have dx changes, we're going to do this whole thing with respect to x. And so our radius, notice these are vertical values. Those are basically our y value, or f of x, but we want that to be x squared, and our radius is x squared. On the other side though, all of our radii are the x value, but since we're building it vertically, we're taking slight changes in y, those are all dy, and so we need our x in terms of y. And that means that we're getting plus or minus the square root of y. But again, I only want one side of my curve. So I'm only going to use the positive side there, which is marked in green, and so my radius is the square root of y. My area then for each of these, for the first one would be pi r squared, which is pi x squared squared, or pi x to the fourth. For y, I've got pi square root of y squared. And so finding my volume, I'm going to come back up to here and here. In terms of x, we look at my limits of integration. I'm going from 0, let's just say we're going to 2. So going from 0 to 2, I can write my pi in front of there, just bring it out. My x squared will give me x to the fourth dx. The other one, which is rotating in a different direction, these are the y values now. Our building, maybe we'll go up here to 4. It wasn't really given to us, but let's say we're going from 0 to 4. Those have to be y values. We'll make sure we have pi, and we have our radius squared. Now in this case, that will just be y as we cancel that out, and then dy. Notice also that these volumes are not going to be the same. These are just a completely different shape, and so they're going to be giving us different values. We have to be careful to rotate them in the direction that our instructions in our problem tell us to rotate them.